A warm welcome to you all to the fourth phase of the webinar series, Space for Youth, organized by Students for the Exploration and Development of Space, University of 𝗰𝗄𝗶𝗵. My name is 𝗰𝗶迄ះand I will be your moderator for the day. The topic that will be the focus of today's webinar is To the Space through the James Webb Telescope. Let me introduce our guest speaker for today's event. He's a very special person. He was educated at Royal College Colombo and he received his bachelor's degree with honors in physics in 1976 from University of Colombo. He commenced his career in astronomy at the University of Pittsburgh, where he completed a master's degree in astronomy. He also read for a PhD at the Australian National University. He completed 3 first doctoral appointments at Union Institute of Advanced Study in Princeton, Dominion Astrophysical Observatory in Canada, and NASA Goddard Space Flight Center. He also worked in many fields of astronomy in several universities. He is the former chairman of Sri Lanka Association for the Advancement of Science and for Senior Research Scientist of Astrophysics. Also, he is a member of the International Astronomical Union. Please welcome Dr. Kavan Ratnatunga, President of Sri Lanka Astronomical Society, to address the gathering.
Thank you for that kind introduction. Today, I'm going to talk about the James Webb Telescope. Unfortunately, I have not been working with it because after the Hubble, working with the Hubble for 10 years or 12 years, I retired back to Sri Lanka. Anyway, I found lots of information of the James Webb Telescope, which I will present today, and we can open up for discussion after that. Okay, so observing from Earth, we can see very spectacular skies if you are in the correct place without rain clouds. I mean, those days you could see a view like this from Yala when it was clear, but nowadays there's too much of rain to see a spectacular view like this, and you need very dark skies. But in 1990, the space telescope, the first of the space telescopes were launched. This had been planned for many, many years and finally launched on April 24th. It has an orbit of about 300 kilometers above the Earth. Now, this is the telescope. It's about the size of a bus and it was sent up on the shuttle. And one thing that happened soon after, we discovered that there were errors in the manufacture of the lens, of the mirror. And luckily, because this was on Earth, in Earth orbit, we could go up in a subsequent shuttle in December of 1993 and repair this Hubble Space Telescope in orbit and get it back to the specifications that we had expected for it. So the Hubble before and after repair was a lot different. The pictures on your left, a picture on the left is the same galaxy observed before, and the picture on the right is the same galaxy observed after the repair. So the Hubble was successfully repaired in orbit and now has been in orbit for more than 30 years observed in the sky. Its only initial expectation of lifespan was about 15 years, but it has, with technology and clever planning, it has now lasted for more than 30 years. It has given us spectacular views of lots of things and a lot of science. You all may have seen the Orion Nebula through the small telescope, but this is a photograph of it through the Hubble. This is one of the most famous photographs that the Hubble took of what they call the pillars of the Eagle Nebula. It was very nicely created and became the iconic picture for the Hubble. This is a picture of planetary nebula, Southern Ring Nebula. I showed this because one of the initial photographs from the James Webb also is of the same Southern Ring Nebula. These are colliding galaxies. And this is the Stevens Quintet, also object that was observed as in the first release pictures of the James Webb. The Hubble did a lot of observations, and this is an image of the Hubble Deep Field in 1995, when I was very actively participating in observations with the Hubble 𝗰𝘁 camera, and this was taken with a large number, about 10 days of observing with the 𝗰𝘁 camera. It was a data set that I remember analyzing with the Hubble. Right, during that time, we had a medium deep survey, and this was one of gravitational lenses that we discovered with the Hubble telescope. It happened to be the first one discovered, and I was happy to get my name on it, or at least credit for discovering it. There was another lens which was discovered around the same time, and they from the first initial report. The medium deep survey, which was a Hubble key project, discovered about quite a few lenses in the next few years, and this is a press release that we put out around 1998. In 2004, just around the time that I left and came back to Sri Lanka, this was the Hubble Ultra Deep Field, which was observed with the new instrument of the Hubble Space Telescope, which was 𝗰𝘁. So today we are going to talk about the Hubble with the JWST, which is called James Webb Space Telescope. Hubble was named after a very famous astronomer of the 1920s, Edwin Hubble, and James Webb Telescope was named after an administrator of NASA who did a lot of contributions to develop astronomy research. So one of the main things about the two telescopes, one is that the Hubble observed in the visible light. It had UV light as well as near infrared. But the James Webb is basically a near and mid-infrared telescope, which does not observe in visible light, because this was the range which had not been previously observed at high resolution. The Spitzer telescope observed it at a lower resolution, but clearly we wanted to get higher resolution images. You can compare the Hubble with the James Webb, like in this picture. There is the Hubble mirror is 2.4 meters, 4.5 square meters. And the James Webb mirror is 6.5 meters across. And it's a segmented mirror. It has a large number of segments, and it is 25 square meters. So it has a light gathering power, which is about 5.5 times the Hubble telescope. And just for comparison, a 6-foot person would be about this size. So you are looking at individual mirrors of the James Webb, which are about 2 meters across. The artist a picture of the James Webb. It's a NASA, which is a National Aeronautics and Space Administration of the USA, the Canadian Space Agency, and ESA, which is European Space Agency. It's a collaborative effect of all three space agencies. One problem of creating such a large space telescope is how to launch it, because most launch devices or rockets that we have cannot take such a large instrument, and it required us to the scientists to actually design an instrument which could be folded, and with it creates a lot of technical problems of having to fold it and make sure that you can unfold it in space without creating any glitch in the process. So it was a very dangerous operation. And the first 20 days or something when it was being unfolded was a critical time, because if any one of those operations did not operate properly, it wouldn't have, the whole function of the telescope would have been lost. So the contribution of ESA was the launch of the the James Webb Telescope from their launch site in Ghana in South America. And so the thing was taken from California, where it was built, by ship to Ghana and launched on the 25th of December last year. After launch, this is one of the last photographs taken of the James Webb in Earth orbit from the last piece of equipment that separated from it. The last booster which sent it out on its journey to the Lagrangian point 2, where it would be observing. One of the problems of that is that if there was any defect either in the deployment of the space of the James Webb Telescope, or in when we discovered after observing at the Lagrangian point, there was no ability or capability of repairing it like we repaired the Hubble Space Telescope. So that was a major concern, and everything and all the mistakes that we learned were not repeated when making the James Webb. This is the operation of the Webb telescope unfolding from a real rocket-shaped thing. First, the solar panels are unfolded, and then the sun shield deployment. The sun shield is tensioned behind it. Secondary mirrors and support unfolds. Then the primary mirror are deployed and fully unfolded. And this whole complicated sequence, which took about 2 weeks, more than 2 weeks, I think, was completely successful with absolutely no glitches on its way. So it performed exactly as expected, and we didn't have, the scientists did not have any surprises in the process. So where is the James Webb Telescope? Unlike the Hubble, which was 300 kilometers from the Earth, the James Webb is at Lagrangian point, which is about 1.5 million kilometers, about 1 million miles from the Earth. It's so in this graphic, I show the Earth with the moon going around it. It is not to scale here. So the moon is orbiting the Earth, and a lot further out, about 4 times the distance to the moon, is Lagrangian point 2, which is a special position orbit where the telescope has been placed so that it would be, it will go without, we always can be pointed away from the sun. One of the problems with the Hubble, which was in low Earth orbit, was the fact that we could only observe during half of the orbit. So the orbit was about 90 minutes. And we lost about 40 minutes of that time, or more than that, 45 minutes of that time, because we were in the illuminated part of the Earth, and the telescope could not observe during that time. The James Webb being at far distance from the Earth, it will not be polluted by Earth's light, Earth light or moonlight, and it has been shielded from sunlight so that it could observe properly in a dark atmosphere, dark environment. So this is the orbit, L2, nearly 1 million miles from the Earth, and relatively unobstructed view of the universe. So let's see what exactly this orbit that we talk about. Okay, so this is a small animation of the orbit of L2 relative to the Earth. You can see that L2 and the Earth rotate about the Sun, with the L2 taking us sort of keeping up almost with the Sun. And now we shall see what that was the orbital distance. And if you take a side view of the L2 with respect to the Sun, we see that it is always has the Earth on one side and the Sun. It always faces, the observing part of the telescope always faces away from the Sun. It's not exactly in the same place, but it orbits in a way that it never points towards the Sun. And that way it can be get a good observations which are not affected by sunlight or by Earth light. So there are two sides to the James Webb Telescope. The observing side, which is the side that the mirror is and observes the universe. And the other side, which is the sun-facing side, which has the solar panels to generate energy to run the telescope and communicate with the Earth. So there is here, we have the science panels, a primary mirror, secondary mirror here, and a huge sun shield with separated shields so that it can be completely isolated from sunlight, multiple layer shield to isolate it from sunshine. The unfolding of this shield was one of the most complicated exercises of deploying the James Webb. So the sun-facing side has the antenna to communicate with the Earth, and it has the solar panel power array to operate, get electricity to power and steer the telescope. So there is one cold side and a hot side. So all the communication stuff and the solar panels are on the hot side, and the cold side has the observing telescope. So here, the hot side, it is at very hot. It's about 85 degrees Celsius, almost close to boiling point. It has all the communication, solar panels, communication antennas. And at the other side, which is the cold side, we have it at minus 233 degrees Celsius. So this is extremely cold, and at about 388 Fahrenheit or 308 Fahrenheit. All the science instruments, detectors, and mirrors are on this side. So you can see there is a huge difference between the hot side and the cold side temperatures, and that is required for doing proper infrared observations. So you communicate with the James Webb Telescope through the dark side, and all the things are downloaded to Goldstone in California, as well as the Hubble Space Telescope in Baltimore, Maryland. So the observations are taken and then transmitted down from the telescope. So this is, we are going to do infrared observations. So if you take the electromagnetic spectrum At very long waves, we have radio waves, and that would be a radio telescope. After that, we have microwaves. And then you have the far infrared, near infrared. So the James Webb is basically operating in this near infrared region. The Spitzer Space Telescope, which was a telescope that was in orbit about 10 or 15 years ago, operated in far infrared, but it was a smaller telescope and therefore had less resolution than the James Webb. And the Hubble basically observed mostly slightly into the ultraviolet, mostly in the visible, and only very little into the infrared. Other telescopes would be like Chandra to observe in the X-rays, and there have been gamma ray telescopes as well. So you can't put a telescope up to observe over the full range of wavelengths, and you basically design them to be specialized in observing a certain range of wavelengths. So you can, and one of the reasons for the infrared is important is that the universe is expanding, and as you go further out, the galaxies are moving much faster away from us according to the Hubble law. And therefore, when an object moves away from us at higher speeds, the visible part of the wavelengths of light get redshifted into the red, and therefore they would come in, and what is visible light when it left the telescope would come in and be observed from Earth as infrared radiation. So you are actually doing visible observations of very distant visible range of wavelengths, but in highly redshifted galaxies. So why the infrared? And this is a image of why we expect to see the infrared. This is a sort of simulation, not actual photograph. But when you look at through the infrared, all the dark clouds which you would have normally seen only, which are big regions which absorb all the visible light, do let in the infrared light. So if you have an infrared telescope, you can see through the eagle pillars and see through them and see what is behind them. And in the process, you are getting light which goes through these dark clouds, and those dark clouds will be absorbing certain wavelengths, and you can, in that process, study those dark clouds, what is getting absorbed, because those dark clouds are the ones that contract to create new stars. So you are observing dark clouds, which are the things that sort of create stars in the new stars, and therefore you are studying the material that is used to create stars. So there are lots of applications of infrared telescope. So there are a number of instruments on the Webb Science Instruments. There is a infrared spectrometer, a camera, and a faint object, a sort of infrared spectroscopy as well. So similar to the Hubble also, which had about 3 instruments operating at the same I could operate at the same time, but focusing on one and in parallel with the other 2. So this range is that these 3 instruments are observed in the near infrared, and this is in the near infrared and mid infrared ranges. So So these are the wavelengths in microns, from 1 micron in wavelength all the way up to about 25 microns. So visible light, the near infrared reveals cooler red stars, galaxies, and the dust becomes transparent. Mid infrared is used to observe planets, comets, and asteroids, dust warmed by sunlight, and protoplanetary disks. So these are details of the Webb space instruments. I'm no specialist in the subject. So basically you have cameras to take photographs of the sky or the space over a small region. Spectrographs to observe the light distribution as a function of wavelength, and coronagraphs to block starlight and allow the observations of planets orbiting nearby stars. So transit observations. Oops. Okay, so let's say a planet goes across a far out star, and these planets have been recognized by small wobbles in the star's orbit. And we now have about 4,000 or so extrasolar planets which have been discovered. And you can predict when these objects would go in front of a particular star from Earth-based observations. And so what you want to do is, with the Webb telescope, you'll be observing these stars at the correct time when you would expect at such a transit. And depending on how large the planet that goes across, you would get a blocking of the starlight, which is picked up by the Earth. And with the James Webb telescope, you can also look at the spectral light of that stuff that is coming on. And with that, you know what starlight looks like, and you know what you observe from around the thing. So you can interpret from it what the atmosphere of that planet that is orbiting that star would be absorbing, and by which you can actually get some information of the composition of the planet's atmosphere. So this is what the transit spectroscopy would do. It would basically observe a planet transiting a star, compare the starlight with the spectrum, which has a lot of lines, with the light that is observed during the transit, which is the spectrum with those same lines, plus a lot of additional lines caused by absorption in the planet's atmosphere. And from that, you can determine what the planet's atmosphere would have absorbed, and therefore find out what the content of the planet's atmosphere. You have very many systems which we know about, which we have discovered. There are star systems like the TRAPPIST, which has about 6 or 7 planets orbiting it. And there is a lot of interesting observations which are to be expected by observing these planets going across things. You'll be able to observe whether they have carbon dioxide, water vapor, methane, ethane, and a lot of things depending on the spectra that you are going to observe. And if you see carbon dioxide and water, those planets may be harboring life, and they sort of become targets for other observations. So the orbit that will sort of indicate what the planet's atmosphere may have had, which is absorbing those wavelengths. So you can also study the life cycle of stars from and observe very small stars, which are known as brown dwarfs, which sort of emit mostly in the infrared regions of the things like even the Orion Nebula. You may be able to see the accretion effects of black holes. And the next thing that you'll be able to see is far deeper than we could do with the Hubble in seeing the most distant parts of our galaxy, of our universe. So with the Hubble, we would have seen to a certain distance. With the James Webb, you see to a much further distance. Now, this is sort of a comparison. This was the image that we got with the Hubble of this small galaxy, which is not very clear. With the James Webb, because it's a much bigger telescope, which can resolve much finer, the Hubble had only a 0.1 arc-second resolution, 0.1 to 0.15 arc-seconds. But with the James Webb, you have much bigger CCDs, much bigger arrays. The Hubble had an array of about 2000 by 2000 pixels. The James Webb has a much bigger array or a multiple of arrays, and you see much more detail than you see with the Hubble of small objects. Gravitational lensing is also going to be a big press of observing with the Hubble telescope, with the James Webb telescope. And what is gravitational lensing? That's like the object that I showed you with the Hubble, which I discovered back in 1995. It is when a very distant object is aligned to about 0.1 arc-seconds, which a distant galaxy, sort of a galaxy, a very heavy galaxy, or some black hole. The light that comes from this galaxy is bent by the gravitational field. That's an effect that was predicted by Albert Einstein, and that's why it's called, it was an Einstein sort of predicted that effect from the his general theory of relativity. In his time, he never thought we would be able to observe it. One of the proofs of general relativity was actually observing stars close to the sun during a total eclipse of the sun and seeing their position shifted. That was one of the things that was observed in 1919 and confirmed the probable reality of Einstein's general theory of relativity. Back around 20 years later in 1929, Zwicky sort of predicted that the same sort of gravitational lensing, which was observed near the sun, could be seen from large galaxies bending starlight, but the technology at that time was far too little for us to expect to observe it. The first gravitational lens was actually observed only 40 years later in 1979. And after the Hubble went up, and there has been a lot more gravitational lenses discovered, or observations followed up with gravitational lenses discovered from large survey telescopes on Earth. So what happens here is that you have the Earth here, this getting thing, and you get multiple images. If you have a spherical ring and the object is slightly offset from the center. If it's exactly in the center, you get an Einstein ring. If it is slightly offset, you get two objects. And if the potential is elliptical, then you have two axes and you get a quad, like I showed you before. That is a sort of almost an Einstein ring. created by a distant galaxy around a distant object, which is a galaxy itself, getting creating Einstein ring around this galaxy. So up to 1990, we had ground-based telescopes which could observe up to a certain distance. In 1995, the Hubble Deep Field extended that distance. The Hubble Ultra Deep Field extended that distance even further. There was an even deeper field in the infrared done in 2010 when the infrared camera was attached to the Hubble Space Telescope. And the James Webb is expected to even observe up to much closer to the redshift, so that with the Hubble ground base, you go up to about 6 billion years, and or a redshift or 6 billion years, not since the origin of the universe, which are 13 billion years. Then at a redshift of 4, which is about 1.5 billion years from the Big Bang, you see then about a redshift of 7, you are looking at objects which are about 800 million years within the redshift, and then you can go to even 400 million years at a redshift of 10. So that is what I would like to tell about the Hubble. The Hubble is going to be, the James Webb. The James Webb, there is an infrared telescope which looks at small regions of sky. There is going to be a wide field infrared survey telescope, which was originally called 𝗰𝘁, which has been renamed with the name of Nancy Grace Roman, who was a famous astronomer who discovered a lot of observations were interpreted as dark matter, was actually her observations that are of external galaxies that went to the discovery of dark matter. And this telescope will be named after her. It's expected to be launched in 2027. That's a target date, but I'm sure it will most probably get delayed. The Hubble was delayed at least about 10 years or even more. It was originally supposed to launch in 1983 and was finally launched in 1990. The James Webb, I think, was supposed to launch in 2015, I think, or even earlier, and then finally launched in 2021, and observation started in July of 2022. I will stop sharing, and I will share another shorter video of, let's start share. Okay, why isn't this moving? Okay, it's taking its time. Okay. So in July of this year, we started observing with the James Webb, or it was observing, it took at least 6 months really to start the first observations, and after calibrating the telescope, because you had basically a large 18 separate mirrors which had to be all focused to give a single point of light. And after that operation was completed successfully, this was the Webb's first deep field, and this is towards a cluster of galaxies, and that you can see in this cluster of galaxies, you can see all these little galaxies in this field, which have been twisted around this galaxy, this cluster of galaxies, by being gravitationally lensed. Either there may be closer in, you will find multiple images of the same galaxy, and further out, you will find just a weak lensing, which is where a galaxy would be twisted so that it looks like it's wrapping around this cluster of galaxies. The weak lensing has become a very strong and powerful tool to study the universe at large and at larger distances than you could do without it. So the lensing usually operates like a big telescope in itself to observe the more distant universe. This was an observation of an exoplanet, and as expected, the scientists were able to observe water vapor in the atmosphere of the planet that was orbiting the star there, and therefore it gives a lot of hope that those planets do have water, and those planets can be used and may have life of some nature. So this is becomes the first evidence that there is water in extrasolar planets that have been discovered. So much more, this is just the initial observation of one of them, and there will be much more observed in the next 10 or 15 years. This is infrared image of what I previously showed, an image with the Hubble. So this is the same southern ring nebula. You see a lot more structure than you see with the Hubble, which could only see up to about this distance, and you see much more structure beyond that in different wavelengths of light. This is again a cluster of galaxies that I showed previously with the Hubble, and you are now actually seeing through them, in fact, not crowded by the dust which is in the plane of these galaxies, and seeing even objects which are beyond the galaxies and what. So you see the faint extensions much clearer with the James Webb. That's a sort of high resolution image of a star forming region, also observed with the near infrared telescope camera imager. Okay, so that's what I'm going to talk about today. I think I took about 40 minutes. And I now open up stop sharing and open up the floor for discussion and any questions on what I presented today, or even if you have some general questions, I'm quite willing to answer them. But let's start with questions about today's presentation. And after that, we can go to more general questions if anybody has a specific question they want to ask. Okay, over to you.
Okay. Thank you, sir. Now it's time for the Q&A session. There are some questions with me, which was raised by the participant.
Okay.
I'll read those now.
Okay. Are they on the
The
chat?
first question is
it on the chat? Or it's before the chat?
Sir?
Is it
Before
on
the chat, sir.
Okay.
The first question is, what is the mechanism used in those lenses of James Webb Telescope to capture those sharp images?
Right. So to capture a sharp image, the two things, the main thing that you need is that if you are within the Earth or within the Earth's atmosphere, the Earth's atmosphere is turbulent, and therefore whatever object that you get from the star or the starlight that you get, if you look at the night sky, you see it twinkling. Why you see stars twinkle is because there is the starlight is getting obstructed by dust particles in the atmosphere. It gets slightly diffracted by objects, the atmosphere, and therefore, even if you observe from Sri Lanka, for example, all the images will get blurred to about 1 arcsecond. So it's very difficult to look at any object which is smaller in size or a resolution less than which is smaller than 1 arcsecond. From the best sites, which is say like the telescopes in Mauna Kea and in Chile, where you are very much higher than near sea level, and therefore, and there is a very clear skies, you may on certain days get the seeing down to about half an arcsecond and see better than we can. Now, if you are in space, like the Hubble Space Telescope, then you are away from all of Earth's atmosphere. There, you are only limited by the size of the telescope. So the Hubble was 2.4 meters across, and therefore it was actually smaller than some of the telescopes we have from ground, but because it was in space, it could see to about 0.1 arcseconds resolution, which is the maximum you can get from a 2.4 meter telescope. Then the James Webb, because it is 6 meters across, can collect both more starlight, 5 times more starlight during the same time, as well as because it is much larger, you can go to much higher resolutions, maybe about 0.01 arcseconds. So you get 100 times better resolution with the James Webb than you would get from ground-based, and 10 times better than you would get from the Hubble. I'm not exactly sure whether it's 10 times. Each instrument would have its own increase in resolution depending on the detector as well. And the second thing is because you are observing in the infrared, you don't get the problem of the light getting absorbed by interstellar dust clouds and dust which is all over the galaxy, which would absorb the wavelengths of visible light, but will absorb less the wavelengths of infrared light. And because you are observing the infrared, you can get finer images. So those are the two main characteristics of getting finer images. You cannot do it from Earth.
Okay, sir. The next question is, what will be the perspective of James Webb Space Telescope if it was hit by a micrometeoroid? Is there a solution for it?
I'm actually not sure, but I think it could get damaged. If it is a micrometeorite, maybe it won't be damaged so much. It depends on what it hits. I mean, if it hits one of the instruments, then it could be damaged a lot. If it hits the solar or the shield, and the micrometeorite goes through the shield, there may be problems because the shield will have a pinhole in it, and therefore let in a bit of starlight. Hopefully that will not be so big. So it all depends on the size of the micrometeorite. I mean, there are micrometeorites all the way to nano size, which may not affect it. And if it is a millimeter or a centimeter size, it will be much more problematic. So it's like the same dangers that we have in Earth's orbit, of things like the International Space Station. So a certain amount of statistics is available as to how crowded this space is with micrometeorites and larger small meteorites. Earth's orbit is much more crowded with those things because the Earth is attracting them into the Earth, and therefore you will find a larger concentration closer to Earth's orbit than you would get a million miles from the Earth, which is also helpful for the James Webb. But it's clearly a factor which will have to be taken into account. I have not actually read up what the statistics and the expected probability of that sort of damage is. I'm sure you'll be able to find it on the internet if you search for it. Okay. Okay, next question. You are muted.
The next question is, what is difference of James Webb Telescope rather than the Hubble telescope?
Okay,
How is the efficiency?
I think I explained that in many slides. One is that it is much larger, and the fact is that it is observing in the infrared. So that I showed a number of slides explaining that during my talk.
How is the efficiency? Since the Hubble telescope is more sensitive to blue light than James Webb telescope, can the images from both telescopes be combined to produce a more detailed image?
Yes, I mean, that is something that would be done. I mean, each of these instruments observe a different range of wavelengths. And the science actually comes from the full range, from the infrared, maybe even to the X-ray, all the way to radio waves. So you'll be getting observations from the full range. Radio waves are mostly done from ground-based observations because there is less, the atmosphere gives less problems to the radio telescopes, and radio telescopes, by the fact that the wavelengths are larger, have to be much larger than optical telescopes, and therefore they are even more difficult to get up into space. So radio astronomy will continue on Earth observing the large wavelengths, and then you get to infrared, far infrared, near infrared, Hubble observing the visible. And then you have specialized telescopes like Chandra, which observe the X-ray, and telescopes which observe gamma ray. Telescope also was launched to observe the gamma rays. So clearly the full spectrum of observations are taken and combined. I mean, not necessarily to create images, because images don't really say very much. And most of the infrared images that you are shown are false color because they have been sort of changed to colors that you can actually see and interpret. So, but clearly you take the science information from all those wavelengths to study the properties of the objects they are observing. Okay.
There are some questions in chat box also, so I move to that. Sir, what is the specialty of the honeycomb structure of the James Webb Space Telescope?
Okay, I mean, there is a sort of 6 meter or 8 meter diameter, which is the maximum that you can create with a glass single mirror. Because if you, as you create the glass to be much larger, you get, it has to be much thicker, because if not, you get the edges sort of bending away from you by its own weight. And therefore, you have sometimes create honeycomb structures. And around, the technology was there only for creating things around 4 meters, maybe 50 years ago. They have now made single lens mirrors, which with a lot of more technology, which are about 8 meters. But clearly you couldn't have sent a 8-meter diameter a mirror into space, one, because it would have been very heavy, and the next is that it is much bigger than the launch vehicle. So I showed you the fact that the telescope was made out of a honeycomb structure is a necessity to create such a large telescope. So there are quite a few honeycomb structure telescopes which have been created on the ground for similar reasons of not being able to create very large telescopes. We have got stuff which are now more than 10 meters across. And those are basically because you can connect about 6 or 8 mirrors to form a honeycomb structure. So this technology of creating honeycomb structures was done for ground-based observations and by ground-based telescopes, and by necessity of having to launch it was used for the James Webb. And once you have the technology of adjusting and aligning these
what are the best months to observe Milky Way so clearly in Sri Lanka?
That's a good question. When there is no rain, and when is there no rain, I have no idea. Maybe around March, February, March, that is the sort of clearest part of the year before the southwest monsoon. And definitely you can't see it from Colombo or the places where there is a lot of light pollution. You may have to go to the dry zone, extreme dry zone, which is somewhere like Yala, 𝗰𝘁. I was in Yala in May this year, and I was able to faintly see the Milky Way. Clearly not a spectacular view of it, but I could recognize that it was the Milky Way that I was seeing. And if I was there, not during sort of the beginning of the monsoon, which is what May is, I'm sure you can see a clear view of the Milky Way. You have to go away from light pollution. You have to have a clear view of the southern sky. So I would suspect that you would go somewhere in February or March. And if you just consider, those are the months that most of the pilgrimages are done to 𝗰cie~迄HH, basically because there is less rain during that period and it is considered in season. I took this photograph of the sun rising behind 𝗰cie~迄HH. Some of you may have seen it on YouTube. And that was taken again in March. And that from Colombo, I took it from Mount Lavinia. I have only seen, for the 15 years, 17 years I've been here, I've seen it on about 5 occasions. So it's about once in 3 years that the sky is clear to be able to see that sort of sunrise.
How James Webb Space Telescope maintain the temperature difference between the cold side and hot side? What's the technique?
So the technique is those shields, as I showed you in that thing. There is a sun shield, and there is multiple layers of the sun shield. There's about 5 layers of sun shield, sort of, which reduces the amount of sunlight. And the second thing is the orbit. The fact that it is at an orbit, which you can have the telescope always pointing away from the sun, so that you could always have one side towards the earth to be able to communicate, and away from the earth to observe. So that way you cut out both earth light and sunlight and moonlight, because the moon is also on orbit from the earth, will be also behind. So you have almost complete blocking of the bright objects in a neighborhood, which is the sun, moon, and the earth, and you see into the darkness of space with a very low temperature.
So can you describe Hawking radiation again?
Pardon?
Hawking radiation.
Hawking radiation. Okay, now we are going completely out of what we were talking about. Hawking radiation is what Hawking predicted would happen close to a black hole. And you basically have, if there is an energy, right, a packet of energy can break up into elementary particles. So you can suddenly get electron and a positron, which is the antiparticle, being created in the neighborhood of a black hole. And if by chance the antiparticle gets absorbed or gets gravitationally attracted to the black hole, and the particle escapes from that near the black hole and can get radiated. So they have very slow process, which Hawking's predicted could happen, of particle-antiparticle pairs getting created in the neighborhood of black holes, in the event horizon of black holes. The particle, one of the two particles getting absorbed by the black hole and the other getting radiated away. If you have this generally the particle and antiparticle pair forming in deep space, then they would quickly annihilate or the antiparticle will annihilate by hitting against the particle, and the actual particle might not annihilate depending on whether it hits against the antiparticle. But clearly this asymmetric radiation could happen by the phenomenon which was predicted by Stephen Hawking, and the radiation is named after him for predicting that you could radiate out of a black hole. Initially, it was thought that everything that goes into a black hole never comes out, and this radiation would ensure that in trillions and trillions of years that the universe, if the universe exists, all the black holes also will evaporate and we will have only energy. So this is so far into the future that we won't be able to know about it. Okay. Any other questions?
Yes, sir. Stephen Hawking says in his books that when universe expand and time move forward, things will get disordered state. And he thinks that when universe attract to that singularity point, it will make things back to ordered state. But his student proved that's wrong. Please let me know your thoughts on this.
Yeah, I mean, originally when let's say in the 70s or even the 80s, we didn't know whether the expansion of the universe that we are observing now is going to slow down and finally become what they call a big crunch, which is that it will slow down to a point where the gravity will re-attract the objects and there'll be a big crunch and everything will come back, and then you would all come back to a singularity and then create another big bang. So that was sort of, we didn't know which of those two states, whether we would continue to expand or whether we'll contract after a certain period of time. But recent observations in the late 1990s has observed that we are not only that we are expanding, that the expansion is actually accelerating. And therefore, it is very unlikely that what we are observing will ever contract into a singularity. So the current anticipation is that the universe will continue to expand and expand, the expansion rate growing, and that is attributed to what is labeled dark energy. And the dark energy, which is a factor called lambda.
How far back will Webb see?
Okay, so the Webb would see back to about, you can't see beyond, 400,000 light year, light year or years after the Big Bang, because there are no galaxies, there are no things, and the thing is opaque. You cannot see beyond into that. But up to that, we know unlikely that we'll see it so far, but most probably we'll be able to see, as I showed in that final view graph, up to about billion years from the Big Bang. Now, when you are looking at objects which are billion years from the beginning of the Big Bang, one has to remember we are seeing light as was given out by those objects 12 billion years back. But those objects that we are seeing now, we are seeing it as it was a billion years from the Big Bang. So when those galaxies or those objects were only a billion years old, or billion years from the redshift, but those galaxies may not be there even now, because they would have evolved in the subsequent 12 billion years. And they would also have gone away from us with the expansion, and they would be now 45 billion years away from us. So in a way, we are looking at objects which are now 45 billion years away, even though we are looking at light, which has come to us from 12 billion years in the past at an object as it was 12 billion years ago. So it all depends on what you talk of, what you see. What you're saying is not the present. You're looking back, not at what there is at that position now, but what was there at that position so many billion years ago, 10 billion years ago. And the more distant you go, the more further it actually would be because of the expansion of the universe.
Next question is, sir, I have heard that radiation from the early universe is now observed as microwave radiation, and that information about the early universe is deduced by observing the cosmic microwave background radiation. So how does the James Webb Space Telescope, which is sensitive to IR radiation, reveal fact about the early universe?
Now, the cosmic background radiation is observed by specialized telescopes, and one has to observe large regions of the sky. Sort of most of the survey telescope like WMAP and 𝗄𝗶𝘁 at a lower resolution than WMAP were designed to actually observe the whole of the sky from all directions, so that we could map out the cosmic background radiation and derive all the science that we have derived about the early universe. Now, the James Webb is not designed as a survey instrument. It would only observe very small regions of the sky, and therefore would not be useful for studying the cosmic background radiation. So all these things, you design telescope to do very specific tasks, and you don't try to do everything with every telescope. So that the Hubble was designed for one task of looking in the visual. The James Webb is designed to observe mostly in the infrared. And there were sort of telescopes which were going to be designed, which were to be observed in the ultraviolet. And then like that, further out, X-rays and gamma rays. So you don't use the science that comes out of each of these telescopes does not cover all of the observations that you have taken by other instruments.
So why can't we have a telescope that can monitor American flags planted in the moon in order to dismiss claims made by the conspiracy theorists?
There is an orbital telescope, or I think it's a land sort of orbital telescope around the moon. And if you go on the internet, I can sort of share those links with you. There are sites where you can't see necessarily the flag, but you can see the landing, the lunar lander. The lunar lander is single pixel at the resolution of that observing camera, but you can see the shadow cast by the lunar lander quite some distance during sunrise and sunset, and they have laid those observations one on top of each other. There is a bar on the bottom, and you can pull that bar, and you would see the telescope, the shadow of the lunar landers as it elongates during sunrise and sunset. So in a way, we have actually observed physical evidence of the landing. But you know that people who are conspiracy theorists will continue to talk about conspiracy theories until man goes back to the moon, lands, and actually stands next to one of these flags and take a photograph. So once you believe in nonsense, you continue to believe in nonsense, it becomes almost a religion to them, and to convince them otherwise is very difficult. But there is observational evidence of the landing with respect to the lunar landers, and I have shown it in certain lectures I have given.
Will the James Webb Space Telescope be able to further prove or disprove the Big Bang theory?
I think the Big Bang theory has been sort of accepted, the fact that there is an expansion of the universe, and a lot of things, not necessarily with the Hubble, James Webb, but things like WMAP and the ones that did the cosmic background radiation studies have given us very intricate models of the what happened in the Big Bang, and those models would not be possible unless there's a huge change in the whole physics, if not for a Big Bang. So the Big Bang theory as such has been almost accepted. What the James Webb would do is to start doing spectroscopy of the early universe. And the spectroscopy of the early universe will start giving information about what elements existed in the early universe. And there is something called Big Bang nuclear synthesis, which was originally worked out many, many years ago, maybe 50 or 70 years in the early 1950s. And we could be observing the expectations of Big Bang nuclear synthesis with James Webb observations of the spectra. So we won't maybe directly model the Big Bang and its consequences, but spectroscopically, there'll be a lot of observations that would help confirm the Big Bang theory.
Are gravitational waves more useful than electromagnetic waves in revealing information about the Big Bang?
I mean, gravitational waves are very difficult to observe. They were the first time they were observed maybe about 10 years ago. And it would be a long time before we get, I would say, more information than the optical and other infrared telescopes from the gravity. But the gravity, they are all explore different regimes, and each gives their own constraints into our model of the whole universe. And all these little observations of each different regime have to be incorporated into a single model for the universe. Unfortunately, we don't even have a single model for the universe. We have general relativity, we have quantum electrodynamics, and we have the sort of standard model of particle physics, sort of complementary views of different aspects of the universe. And actually, to go ahead at some point, we have to start merging these theories into one big grand unification, as they call it. Unfortunately, people thought about 50 years ago or 40 years ago that string theory would be able to combine these theories into a unified theory, and they were talking about 26-dimensional space-time into a which would explain the universe as a single theory. But none of those theories have actually explained things completely without creating other problems. So none of the things are sort of, they are getting closer maybe, but not close enough for us to accept that string theory is the final solution to a grand unified theory. I think what you have to consider the fact is that the universe is being observed with different in different directions or in different dimensions. If you take a cylinder and you observe it pointing towards you, you will observe a circle. If you look at a cylinder in 2 dimensions from the side, you will see a rectangle. If you ask what a cylinder is, it's neither a circle nor a rectangle. It's a cylinder. In a higher dimension, it's a 3-dimensional object which you are looking at from 2 dimensions. There was a nice graphic I saw recently shared on WhatsApp on this. And so that is what is happening. We are looking at the universe with with general theory of relativity and with the standard model of particle physics or cosmic electrodynamics in different ways. And we are getting different views of the universe, which we have looked at in different directions, like we looked at a cylinder in different directions. And we are getting slightly different views, which are sometimes not compatible with each other. But that does not mean that there isn't a theory which unifies everything. It's just that we have not discovered it. After all, it took about 300 years after Newton for Einstein to come up with the general theory of relativity to unify at least space and time. And it may take a couple of 100 years more for us to get a general theory of the universe. And that is the way science progresses. It progresses in small ways, and we'll have to wait for the next Einstein to come around and unify the theories. But as we get more and more observations, each of those observations put more and more constraints onto the theories that can be propagated, because you have to be consistent with all the observations you have, whether it's from gravitational wave observations to infrared observations. So as we get more observations, actually we are now more in the observations, where we have more observations than we have theory to unify all these observations. And this was the sort of regime that science of physics was about 150 years ago in the 1880s, when we have a lot of observations about the sun. We had observations about, we knew a lot about atoms, but we had sort of started by Mendeleev discovered the periodic table, but that was all just 150 years ago. We have progressed a lot since then, but it would be probably another 150 years or more before we become closer to the truth. Unfortunately, each of these problems are becoming more and more difficult, and more funding is required. If you can, I can remember back in 1970, they were talking about fusion energy being available in 30 years' time. It is still in the 30 years in the future. If you ask anybody about fusion energy, it has not come closer to us because of the technological problems. Maybe there'll be a breakthrough and suddenly we'll get it in 10 years, but it is the way science works.
Why does the sun shield have 5 layers?
That is because anything that has 1 layer, 5 layers will exponentially, if one layer absorbs, reflects 99% of it, 2 layers will get 99 times 99, which is 0.01. First layer, if it takes out 99%, will let in 1%. That 1%, if it lets out another 1%, the second layer will take out another 99% of the 1%, and it will down to 0.01. You take out, put a third layer, and it will be 0.0001. The fourth layer will make it 0.00001, and the fifth layer will make it 10 to the power 10 of 1% of a percent. So 10 to the minus 10 of 1%. So basically each layer, I don't know exactly how much each layer takes out, whether it's 99% or smaller than, more than that. But that is why you have multiple layers, because each layer multiplies how much it takes out.
Why is the star Methuselah older than the universe?
Pardon?
Why is the star Methuselah older than the universe?
Star what? Star?
Methuselah.
Protostar. What? I couldn't understand the question.
Why is the star?
Is it on the chat?
I send it to the chat, sir.
Okay. Okay, you are putting it on chat. What is Methuselah? I have no understanding. What is that star? I don't understand the question. What is Methuselah? Ask. I have no idea what you're talking about.
What are intergalactic mediums?
The intergalactic medium is the region between the stars and or the intergalactic is galactic would be beyond our Milky Way galaxy and between us and say the Andromeda galaxy. And that region, there would be a sort of a smaller and smaller concentrations of electrons and other fundamental particles. There could be individual stars floating around that area. There could be black holes. There could be anything that escapes from galaxies which could actually populate that area. But that area being so large, you wouldn't very rarely see an individual object there. If there is a black hole, if we are lucky, we might spot it if it goes in front of another galaxy, then you would see the gravitational lensing effect of that black hole. Nothing like that has been observed as yet. Other than that, there would be intergalactic space would be fairly much of a vacuum, but not an absolute vacuum, because there is radiation of various types which are passing through that area, particles as well. So it's a sort of empty void with a certain amount of thing. If you take our intergalactic area within the local cluster, then that would be a bit more higher concentration than between clusters. So you would have a certain amount of things between what you call interstellar space between stars, and you will have less between galaxies, and they will have even less between clusters of galaxies and so on. And then you would have, there are voids in the distribution of galaxies in our universe, and you will have extremely little in the voids within those clusters of galaxies or regions where clusters of galaxies form. So, but it will probably never get down to absolute vacuum where you don't have any particles at all.
It was mentioned that Stephan's quintet shows the light emitted by objects falling into a supermassive black hole. Could you maybe show that region and explain the possibility of capturing images of black holes?
Okay, so the issue is that one cannot observe a black hole. I mean, black hole is something that may be having Hawking radiation coming out, but that is not sufficiently a large amount of radiation that you would see the effect of. What you see as a black hole and what has been photographed as a black hole is the ring around the region around the black hole where gas and maybe stars are falling into the accretion disk and getting absorbed by the black hole. So you can, for example, around the center of our galaxy, where we have a black hole which has a mass of about 4 million solar masses, as far as I remember. And you find stars which are at a certain distance, not too close that they will get picked up. But because of the very heavy black hole in the center, they are going around that black hole at very high velocities. So you can observe the effects of a black hole and see and interpret how big it is and how large it is from the orbits of stars around the black hole. So it is in that way that you would be, probably with the James Webb, you may be able to see higher resolution Sagittarius A, and therefore get more observations of the center of our galaxy than you could with other telescopes. So then you would be able to observe the stars, get finer measurements of their orbits, and get finer models for the black hole in the center of our galaxy, and similarly may be able to resolve stars moving around other black holes in nearby galaxies like Andromeda. So this is sort of a process of not actually seeing the black hole, but seeing the effects of the black hole.
What sort of a coloring process is involved after capturing the IR images?
Okay, I mean, one thing that you have to understand that even the Hubble images are not taken in multiple colors. I mean, a single image will not be taken which has all three colors. Each 3 colors or as many. Now, what you normally take, you could take images which have a red filter, a blue filter, and a green filter or yellow filter, or whatever the filters that the astronomer wants to observe in. And some of those, sometimes you observe, if you're observing faint objects, in fairly broad filters. And sometimes you observe in very narrow filters if you are looking at particular features of the spectrum that you want to capture. So all these images, which are really black and white because they don't have any color information at all, are then combined to create a color image by creating a certain weight between the things. And all our images that we print on books as color images are also just combinations of 3 colors. So if you finally look at a CCD image or a color image that you are seeing on your screen, you have little dots, each of which have most probably 3 or 4 different colors, which depending on their intensity, you would combine because it's lower than the resolution of your eye, and you would see a single color. If you use a magnifying glass on your screen, you might, or a microscope on your screen, you may be able to resolve the 3 different pixels that are made up a color image. A camera that is taken in your camera, you would have an array which also has 3 pixels, 1 for each color, red, blue, and green. And would be, so when they tell you have a 6 megapixel camera, actually it is actually 2 megapixel array, which is repeated 3 times, slightly shifted from each other, and each sensitive to a different color. And that's how you get a camera which will take a color image. But that is not the way telescopes take images. They take each of the images separately and then combine. That was something that I was regularly doing with Hubble images to create the color images, like I showed for the gravitational lens. And it's quite an art to combine those images to see something which is nice. And that Eagle Nebula, I think, more than the observations, was the artistry of the astronomer who actually combined those images to make that beautiful image of the Eagle Nebula that made it so popular, more than the actual images. So this art of combining single black and white packages are becoming much more sophisticated now.
Okay, sir. If you have any questions, you can unmute yourself and ask the questions.
I see a few advertise this on the Rationalist Society list, and I feel at least a few of them on the list. They may well be interested in asking questions. They wanted to have a similar chat on the James Webb, and I invited them for this lecture if they were interested.
Okay, I think no questions. So Q&A session is now over. Thank you so much, Dr. Ratnatunga. We appreciate you taking your time off to deliver this talk to all of us.
Thank you for inviting me.
That brings us to end of the session. Thank you all for participating and have a good night. Stay safe.
Thank you. Bye. Good night.